Today we're going to take a look at Hess's law. Hess's law says in going from a particular set of reactants to products, the enthalpy change, delta H, is the same whether the reaction takes place in one step or a series of steps. I think what we're going to do is we're going to take a look at some problems, then we're going to kind of come back and see how that applies to Hess's law here. I've got a picture of Germain Hess there. He was born in Switzerland, lived in Russia. So I think we'll go ahead and take a look at a problem here dealing with Hess's law, and we can come back and take a look at his law a little bit and see how that applies to it. So this one says, given the following thermochemical data, and then we've got three reactions. We've got the synthesis of carbon dioxide, the synthesis of sulfur dioxide, and the synthesis of carbon disulfide. And then for each one of those reactions, we've got the enthalpy change for each one of those given to us. And then at the bottom it says, calculate the enthalpy change, the delta H, for the following reaction. So what we're going to do is we're going to use these three above reactions. I'm just going to number these up here. I'll number them, letter them, I guess, A, B, and C. And we'll make reference to those as we go through and work this out. It's kind of like a little problem-solving algebra here. So if I take a look here, and there's not a particular order you have to do this in, but for example, if I look here, I see that we have SO2 as a gas, and up here we have SO2 as a gas, and that's the only place in the A, B, and C that SO2 occurs. So what I'm going to do is I'm going to use that equation where I've got SO2 as a product to come up with SO2 as a product over here. So I'm going to write this equation down that I just up there. Equation B is S as a gas, and the state of matter symbols are very important on these because we're going to do some algebra and crossing some stuff off. O2 is a gas, yields SO2 as a gas. And the delta H for that reaction, it says, is negative, exothermic, 296.8 kilojoules per mole. Now if you notice, in the equation I'm trying to solve for, there is a 2 right there, which means I need two SO2s. So what I'm going to do is I need two SO2s here, so I'm going to have 2 moles of SO2, but I also have to have 2 moles of oxygen and 2 moles of sulfur. Now since I doubled that reaction, this delta H right here, okay, it says it's per mole, okay, so it's for 1 mole. So what I'm going to do is I'm going to double that value since I doubled each one of these coefficients here. So negative 296.8 times 2, let me try that again. Oops. So negative 296.8 times 2. That's going to give me an enthalpy for this now of negative 593.6 kilojoules per mole since I doubled that. Okay. Now I'm going to look back up here at the reaction. So I've got my SO2, this one here, taken care of. Now I'm going to find some CO2. Now the only place I have CO2 is right there. So I'm going to write that reaction down. So I've got carbon as a solid. There's reaction A up there. Plus oxygen as a gas forms CO2 as a gas. Now right here, CO2 is a product, and here CO2 is a product. I just have one of them. So the delta H for that reaction I can write down as given. The delta H for that one is negative 393.5 kilojoules per mole. And then if I look, I'm going to switch to red here. I've got 3 O2s right here, and if you look, I've actually got 2 O2s there and 1 O2 there. If I add those up, that's going to give me 3 O2s right there. So we'll go to, I guess we'll go to, I don't know, we'll go to orange, get a different color here. And we'll look at the CS2. Now the only place I see the carbon disulfide is right there. Now I've got a little bit of a problem because in this reaction here, it's a reactant, and in this reaction here, it's a product. So what I'm going to do is I'm going to take this reaction here, reaction C, and I'm going to flip it. So what I'm going to do is I'm going to put the products on the reactant side. So I'm going to have CS2. And then that's going to decompose then into carbon as a solid. Get my liquid on there for the carbon disulfide. Plus 2 sulfurs as a solid. Now, since I flipped that reaction, when I write this down here, I'm about to flip the sign of that, so it's going to be a delta H of negative 87.9 kilojoules per mole. And now I think I'm going to be pretty good here. I'm going to extend the page here. I want to look at that equation there. And now what we're going to do is we're going to do a little algebra. Okay? And if I look here, I've got carbon as a solid there, and I've got carbon as a solid there. So those two entities then will cancel off because one's on the reactant side and one's on the product side. You can subtract them off of the equation. Okay? And then I'm going to look right up here. I've got 2 sulfurs, as it says it's a gas there. I think that's a solid though. Yeah, this right here is a typo. That should be sulfur as a solid, which means this sulfur here should be as a solid. And that sulfur is a solid, and that sulfur is a solid. Then we'll subtract off of both sides. So then if we look here, what I've got is I've got let's switch to black here. I've got CS2 as a liquid, plus, we talked about that, the 2 and the 1 O2s. 3 O2s as a gas is going to form CO2 as a gas right there, plus 2 SO2 as a gas. Okay? So algebraically, I manipulated equations A, B, and C in this part right here, so I could cancel out and add together and get the reaction right here that I'm looking for. So what we were supposed to find here is we're supposed to find delta H for that reaction. So to find delta H for that reaction is I can just come over here then and add this value, and this value, and that will be the delta H for the whole entire reaction. I came up with a value of negative 1,075 kilojoules per mole. And the negative sign there indicates that it's an exothermic reaction. This reaction will give off heat. Jump ahead, I've got another problem here. That's looking really small. See if I can enlarge that for you. It's looking maybe a little bit blurry, but I'm going to try and use this one here for you. Oh. Okay, we've got the same thing here. Given the following thermochemical data, and then we're given 3 reactions. I think maybe we'll just go ahead and work this out here. Given the following thermochemical data, it says use Hess's law to calculate the enthalpy for this reaction. So we've got the reaction down here we're looking for. So on this one, I'll just number these again, A, B, and C. Right here I've got carbon listed as a reactant. And if I look up here, the only place I see carbon at all is going to be right there in equation B. So I'm going to write that equation down. So I've got carbon as a solid plus O2 as a gas forms CO2 as a gas. And then what I'm going to do is I'm going to make a note here that there's a 2 coefficient there, which means I need to double this reaction by 2. So I need 2 carbons, 2 oxygen molecules. I'm going to form 2 carbon dioxides. So then when I write down my delta H for this reaction, this value right here will be doubled then. That's going to give a value of negative 787 kilojoules. This one here, the thermodynamic data, they didn't put per mole on there, but they very well could have on that one there. But we'll just leave it as that, negative 787 kilojoules. So now I've got a match. I've got a match here, and I've got a match there. So the next one I'm going to do is I'm going to look at my next one on here, H2. I'm going to lower that down a little bit here. My board's not quite calibrated today. H2. And I think the only place I see H2 up there is right here. So, and I've got one H2 here, and I've got one H2 up there, so it looks like I can write that reaction as it is. I think I'll use green for this one here for reaction C. So I've got H2 plus 1/2 O2. Now that's kind of weird, isn't it? The 1/2 O2. But sometimes what they'll do is they'll write these in terms of, how much energy is released in producing 1 mole of water. And if you want to find the energy released in producing 1 mole of water, then you're going to have a half here to balance that out. So sometimes you'll see the half there, and that's okay. And we're leaving this as a 1 and a 1 right here. We'd have to reverse the reaction all, so we can just write that delta H down. So delta H for this one is going to equal negative 296.8 kilojoules. And then I'm going to switch to purple here. We need to produce some C2H2, some acetylene. If I go back up here, the acetylene I have right there is listed as a reactant, and I really want that as a product. So what I'm going to do is I'm going to flip that reaction. So what I'm going to do is I'm going to write down 2, the CO2 as a gas, plus H2O as a liquid, and that's going to form C2H2 as a gas, plus, and here's kind of another weird one, 2 5/2. This looks like oxygen as a gas. So it looks like this reaction here this is the combustion of acetylene. So if we've got 1 mole of acetylene, that's the amount of kilojoules they're given off per 1 mole of the acetylene when we combust that. So now hopefully algebraically things will work out for us here. Whoops, let's go back up here again real quick. This reaction here we reversed, so when we write this delta H value down, we're going to have to make that positive, reverse the sign on that. So this one's going to be delta H is going to equal, looks like a positive 1,299.5 kilojoules. Let me slide back up there real quick, make sure you get that value right. Okay. I'm going to hit extend page here. I'm going to leave that equation right there I can see, and then we're going to algebraically go through and see what we got here. So if I take a look here, I've got carbon dioxide as a gas there, and carbon dioxide as a gas there. So those two will subtract off of both sides. I've got H2O as a liquid and H2O as a liquid. 1 and 1, so those will cross off. And then if I look here on this side, my total amounts of oxygen is 2.5 moles of oxygen, and on this side over here I've got 5/2 oxygen, and 2.5 and 5/2 are the same, so those there will subtract off of both sides. So it looks like I'm going to be good here. I've got 2 moles of carbon as a solid plus 1 mole of hydrogen gas, and that's going to form then 1 mole of acetylene, C2H2, as a gas. So then to find my delta H or reaction, the enthalpy of reaction, I would just take these 3 values here and I will add those up. And on this one, we got a positive value of 216 kilojoules. Positive value means it's endothermic. So there's a look at some problems dealing with Hess's law. So if we go back here real quick and take a look at Hess's law, it says in going from a particular set of reactants to products, the enthalpy change, delta H, is the same whether the reaction takes place in one step or a series of steps. So if we look here, we came up with a delta H at the end for this being like a one-step process. And then up here we looked at a series of steps. And we're able to know that since those are the same, whether we do it in a one-step process or a series of steps, that the delta H is going to be the same for those. So we're able to calculate the enthalpy change for a reaction using some multiple equation thermochemical data.